Good day! I'm Dr. T and welcome to my office. So today I'd like to talk about talking about where stars are. Okay, that's a weird idea. But simply the goal is, how do I communicate if I see something cool up in the sky, where that thingamajig is to somebody else? We need a way of communication, a way of, say, coordinates for where things are, just like we have longitude and latitude for the Earth. So the way we do this is we create this idea. It's not a thing, it's simply an idea of a celestial sphere. And this harkens all the way back to when we actually thought we were the center of the Earth, or center of the universe, I should say. Of course, you know, if you think about it, metaphysically at least, you are the center of your universe. And thus, you know, here goes the idea. So the idea is you take an imaginary giant sphere, and everything in space is projected on the inner surface of that sphere. And thus, you talk about where it is by where something is by where it is relative to that sphere. Now, if you're having problems imagining this giant sphere, go to a planetarium. Well, right now it's spring 2020, so don't actually go to a planetarium, but hopefully you've been there. Hopefully future viewers will not quite understand what that meant. But if you're in a planetarium, you've got the big domed roof, you got a projector in the middle, it's a really funky one, and it projects the stars onto the domed roof. This is exactly what we're doing, but we're thinking about it with, like, you know, a giant planetarium and using that to think about the entire universe. Now, of course, what you put in the center of that planetarium, or that celestial sphere, can actually vary. Usually the most useful one for an individual is going to be their self being in the center of that celestial sphere, in which case usually only do the top half, because, you know, the bottom half, there's ground there, so you can't see it. But you could also put the center of the Earth there, you can put the sun, you can put the galaxy's core there. I'm only going to talk about the first two. Okay, so if we're talking about ourselves, we can imagine, okay, we're standing, or we got the telescope pointing, or whatever. If we think about our head, or wherever we're looking from, straight down from there, going, you know, straight towards the center of the Earth, straight towards where the gravity is pulling, that is your nadir, which is not usually that big of a term that you think about. Usually you're thinking about looking up, so going the other direction, straight away from the center of the Earth through your head. That point, as you project it up on this celestial sphere, that is your zenith. That's the point directly 100% straight above you. Now, we can then look at, you know, you got that line going from your zenith to your nadir, and imagine a disk that's through your eyes that's perpendicular, so it's going out at a right angle. Okay, this is your celestial horizon. Draw a circle on your celestial sphere that's on that plane that's going through your eyes perpendicular to the line from your zenith to your nadir. Now, this is different than your actual horizon, or your true horizon. The true horizon is where you look out, and that's where sky meets land, or sky meets sea. And that's because of the curvature of the Earth and your height. Now, depending on how high you are, that line moves. Or like if you're in a pit or something. So when we talk about this one, we talk about the celestial horizon, which is always at a right angle. It just makes things a lot cleaner. Now, we can start talking about stars with two pieces of information. I need to know how up and down they are, and then how left to right they are. So up and down, we call that altitude. And the celestial equator is 0 degrees altitude. So if I've got 0 degrees altitude, I'm right on the celestial equator. If it's, say, 5 degrees altitude, it's slightly up. Now, that's a circle, so I need one more coordinate to fix myself where I'm on my circle. So what we do this is called azimuth, and it's once again more degrees, but I'm going to take due north, so straight dead north, that is going to be 0 degrees azimuth, and then I'm going to go clockwise around. So east would be 90 degrees, south would be 180 degrees, and west would be, wow, that's a loud car. West would be 270 degrees. And, you know, everything in between is in between. So now I could say my star is at, say, 5 degrees altitude and 97 degrees azimuth, so it would be just slightly southeast of east, or slightly south of east. And that way I can actually point my telescope to it and look at it. Great. The problem, of course, with the system is that all the star's coordinates are entirely dependent on where I'm at. And because the Earth is rotating, where I'm at is actually changing. So it would be nice to have more of a, absolute scale, something that doesn't keep moving, and it's the same for everyone. So in this case, we have a celestial sphere, and we think about it centered not on our head, but on the center of the Earth. Now in this case, we've actually got two versions, because there's a couple of ways of thinking about things. When looking at the celestial sphere, there is an important couple of coordinates. So you can look at the equator extended out. That's your celestial equator, and you can imagine the poles extended out. Those would be your celestial poles. And from those, you can do coordinates going up and down, which would be called declination. So if something is right on the equator, that would be 0 degrees declination. If it's above the equator, that would be a positive number. Below would be a negative number. Now, we need that due north. But of course, now north is up. So where do we put our next coordinates? What is our equivalent of longitude? So for this, we need to introduce a new term, and that's called the ecliptic. The ecliptic is the path of the sun through the sky, or around the celestial sphere. Now, obviously, the sun isn't moving around, we're moving, so this ecliptic is actually the plane of the Earth's orbit. It turns out most of the planets orbit the sun in around the same plane, so they're all going to hang out around this ecliptic. So it's usually right around where we're looking at anyways, if we're looking for planets and whatnot. So where the ecliptic crosses the celestial equator, these are your equinoxes. These are when your days have equal lengths. Now, we're going to use the March equinox, so the equinox that occurs in March, as our point of reference for going left and right. And so in this case, we're going to call it right inclination. And from that, we're able to now start talking about where a star is. Now, I will comment that you could use celestial longitude and latitude, which are referenced using not the celestial equator, but the actual ecliptic itself. So there's a couple of different versions here for this one. But with that information and with some handy guides, you can start pointing out where things are in the sky, aiming your telescopes, and if you have a fancy smancy telescope, it's going to have a couple of features. One, it'll actually have a motor, so it keeps the telescope moving. It's basically a clock motor moving at half speed, so it rotates the telescope as the Earth rotates. Second, it's going to potentially have the ability to punch in what star you want, and it points the telescope for you. But truth be told, if you're doing some, just nice introductory sky watching, don't go spend a ton of money on a telescope. Nice, good pair of binoculars is a good way to start, and then ease yourself into spending money on telescopes. The nice point, though, is if this is a hobby that you want to really get into, you can actually do a bit of research on this one. There's a fairly strong citizen astronomer movement, and definitely some of the comets, etc., have been observed by private individuals. Of course, you also need a dark sky, which, depending on where you live, may be the hardest thing to get. But with that said, have a wonderful day.